All right, so now we want to start chapter 2, which is going to be on solutions. So we'll work our way through this process, first taking a look at mixtures and solutions and how the solution process actually takes place, what solid hydrates are, and solubility of different compounds. We'll also take a look at the effects of temperature and pressure on solubility, and then we'll do some units of concentration and how do you actually make solutions. And then we'll end talking about some properties of solutions. So some of the goals of this chapter that you should be able to do by the end are to be able to define the different kinds of mixtures and be able to explain the influence of solubility of solvent and solute structure, temperature, and pressure. You should also, by the end, be able to express the concentration of a solution. So we have many different ways that we're going to do that. And we're going to look at how dilutions are carried out so that you can dilute solutions to a specific concentration, and then be able to define what an electrolyte is and how the solutions differ from pure solvents in their behavior. So when you have a solution versus a pure solvent, how do things like the freezing point and the boiling point change? So we've talked a lot about matter so far. And so one of the first things that we can do when we have matter and we're trying to evaluate it, we can ask this question: are the properties and the composition going to be constant? If we answer yes to this question, it's likely that we have a pure substance. If the answer is no, it's likely that we have a mixture. So things that would be a mixture, like seawater is a mixture of water with all kinds of different salts mixed in there. Things like mayonnaise, concrete, milk, gasoline, granite, all of these things are mixed components, not a pure substance. So then we can go on and start to separate out the mixture and try to get what we call either a homogeneous mixture or a heterogeneous mixture. We can define them into two different classes. We'll talk about the definitions of these guys. And then we'll talk about further definitions of the homogeneous mixtures into solutions or colloids. So this is kind of the global structure for when we're talking about mixtures. We divide them either into heterogeneous or homogeneous classes, and then if it's in the homogeneous class, it can either be a solution or a colloid. If you have a pure substance, you can ask another question. You can say, is separation by chemical reactions into simpler substances possible? The answer would be yes or no. If it's yes, then it's likely that you have a chemical compound rather than an elemental form. If the answer is no, then it's likely that you have an elemental form of that substance. So water would be a good example of a chemical compound. It's made up of H2O. There's multiple elements that are involved in that molecule, but you can have pure water, right? You can have a bottle that only contains water and nothing else. That would be a pure substance. You can also have elemental forms that cannot be broken down further as well. Things like oxygen, gold, sulfur, any of the elements that are on the periodic table. So we've already spent quite a lot of time in Chemistry 104 talking about this side of the pathway. Now we're going to spend a little bit of time talking about mixtures. So we said our mixtures can be divided into two major classes, the heterogeneous mixtures or the homogeneous mixtures. So heterogeneous mixtures are going to be those in which the mixing is not uniform. So you can physically see regions of different compositions. So if you look at concrete, for example, oftentimes you'll have larger rocks mixed in with smaller rocks, and it's a very heterogeneous mixture. You can look in different areas and it looks physically different. Homogeneous mixtures, on the other hand, are going to be those in which the mixing is going to be uniform. So they have the same composition throughout the mixture. So things like milk, things like sugar water, tea, coffee, they look homogeneous. My can of Pepsi. So they're mixtures. They have multiple things in there, but the whole mixture looks visibly the same. So when we have a homogeneous mixture then that's uniform throughout, it can be divided into what we call solutions or into colloids. So the solutions are homogeneous mixtures that contain particle sizes of a typical ion or small molecule. And so solutions, they can be colored, but they're typically clear so that you can see through them, right? There's nothing, they're fully dissolved, right? So if you have a colloid, these are going to be homogeneous mixtures that contain larger particles in them. So they're not just going to be a small ion or small molecule. They actually have some pretty large particles that range from 2 to 500 nanometers in length. So they're tiny still, but they're much bigger than an ion or a small molecule like glucose. So the colloids, typically, they are more opaque, and you usually can't see through them. So milk would be a good example of a colloidal mixture. So our types of mixtures: heterogeneous or homogeneous. Heterogeneous, listed down here, has particles and things in them that are greater than 500 nanometers. Things that typically they'll separate on standing. So you could filter out probably solid particles out of a heterogeneous mixture. So they typically are murky to opaque. So things like blood, paints, aerosol sprays, you have to really shake them up before you use them. Well, your blood you're not going to shake up, but paints and aerosol sprays, because they probably have solid portions that will actually separate and fall out of the solution. So things that are colloidal, these are our homogeneous mixtures now that look uniform throughout them. You can have things that have larger particle sizes, so the mid-range from 2 to 500 nanometers. Things like butter, milk, fog, pearls. These are often murky or opaque, and they don't separate on standing, so they're not filterable. You can't filter solid stuff out of these guys. So what you will notice, though, is that you can have mixtures that can exist in any phase, right? You can have a gas, you could have a liquid, you could have a solid that are mixtures, right? So we gave an example of like concrete being a heterogeneous mixture. And here you've got butter, which is typically thought of as a solid unless you melt it. Fog, typically thought of as a gas. Solutions then have particle sizes that are very, very small. So again, the size of a very small molecule or an ion, so less than 2 nanometers. Things like air, seawater, gasoline, wine would be good examples of solutions. Typical features then of these solutions: they're transparent to light. They do not separate on standing, and they're also non-filterable. So these two fall into the class of homogeneous mixtures. And then we have our heterogeneous mixture down here. Again, particle size, pretty large. These things can actually separate on standing. So what exactly is the solution process, and how do you predict how soluble something is going to be? Typically, we have a rule for solubility that like dissolves like. So if you have substances with similar intermolecular forces, these are going to form solutions. Substances with different intermolecular forces do not. And so largely when we're talking about these intermolecular forces, we're talking about polarity. So our polarity spectrum ranges from being very nonpolar molecules to very polar molecules, which would be at the very end ionic in nature. So you're going something with no charge to something with charge. Things that have polarity are like molecules. So polar molecules are going to dissolve with other polar molecules. Nonpolar molecules are going to dissolve with other nonpolar molecules. And so we have a definition here when we're making a solution. You've got two things that you're mixing together, and one of those things has to be called the solvent. The other thing has to be called the solute. So typically the solvent is going to be the one that is in greater concentration. So oftentimes you'll see that as being water. If you have a water solution, the solvent is going to be water. So the solvent can vary. You could have other nonpolar substances that are acting as the solvent. It's just typically whatever is in the greatest quantity is going to be the solvent of the system. And then the other constituent is usually going to be a solute. So when you have solid-liquid interactions, typically the liquid is going to be the solvent component, the solid is going to be the solute. So good examples of solvent-solute systems would be the solvent for seawater is going to be the water component. The solute would be the salts that are dissolved in that solvent. You could also have the solvent for air is going to be nitrogen. Nitrogen is a major constituent in the air. The solutes that are also dissolved in that would be things like oxygen, carbon dioxide, methane, all of the other gases that are dissolved in the air would be dissolved in the nitrogen. That's how our solutions are going to be mixtures. So what you will find is that the types of interactions that go on between molecules of the solvent or between molecules of the solute have to be similar in nature for them to be able to dissolve in one another. So again, like dissolves like. Nonpolar things will dissolve in other nonpolar things. Polar molecules will dissolve in other polar molecules. So we'll take an example then of the dissolution of our sodium chloride crystal in water. So the solvent for this system is going to be the water molecule. We know water is a very polar molecule, that the oxygen has the partial negative, the hydrogens have the partial positives. We know that sodium chloride is ionic in nature. So we've got charged molecules here, the sodium and the chloride. So polar molecules of water are going to surround the individual ions and they pull them from the crystal surface into the solution, which makes them dissolve. So you can see for this sodium, the sodium's positively charged, so this is going to want to interact near the negatively charged oxygen. So remember, we've got partial charge here interacting with this full charge here. So this is a dipole interacting with an ion, right? So we said we could have mixtures of our intermolecular forces in the last section. So you can see that all of the oxygens in the water molecules are going to be positioned near that positive charge of the sodium in this case. The chloride, however, when it comes off of this crystal structure, it's also going to interact with the water molecules, and it's going to interact now with the partially positive hydrogens are going to be attracted to that full negative charge on the chloride ion. So these are the intermolecular forces, dipole ion interactions, that are going to allow the water molecule to actually dissolve the solid salt structure. So this is our solid component here. When it dissolves, it's going to be interacting with the water molecules, and it'll be separated just like this. So this represents our solid. This is going to represent our solution state. So the dissolution of a solute in a solvent is the physical change that's called dissolving. This is our dissolving process. The components retain their chemical identities, so you haven't changed the salt even though it's dissolved and the ions are separated here. If we evaporate off the water, then the salt will recrystallize and reform this crystal lattice into the solid form. It's just dissolved now into an aqueous state. So the dissolution then, or the dissolving of a substance in a solvent, has an enthalpy change. So we said enthalpy, remember, is heat that's associated with it. So heat can be absorbed by the solution when something dissolves, or heat can be released by something when something dissolves. So some substances, when they dissolve exothermically, meaning that they'll release the heat. Other substances dissolve endothermically, which means they absorb the heat and they cool the resulting solution. So this is just an example of the dissolving process, or the dissolution of copper nitrate in water. Okay, so if we have our copper nitrate, the solid form of the copper nitrate is going to form a nice crystal lattice. So we can see for every copper, each molecule is going to contain 2 of the nitrates. So this might be 1 molecule of copper nitrate. You can see the next molecule is going to align itself so that the negatively charged nitrate is going to be next to the positively charged copper of 1 molecule. Here's the next molecule in the lattice. Here's the next molecule in the lattice. Here's the next molecule in the lattice. You can't see this full molecule here, but you can see the structure of the solid is very defined, and structurally oriented based on these intermolecular interactions. So in this case, it's ionic interactions, right? So what happens if we put the substance into water? So here's our water molecules. The red represents the oxygen, and the little black tips are representing the hydrogens in this case. So here's our water molecules floating around in the solution, interacting with this solid down here. And when the water molecules come down, remember, these are the nitrates. They're negatively charged. These are the copper ions, which are positively charged. So when these guys come down and interact with the water molecules, this negatively charged nitrate is going to want to interact with the partial positive charge on the hydrogens of the water molecules. So you get this association then when this starts to dissolve in solution. So this will continue. The water molecules will start interacting, and the solid is going to dissolve. And so by the end, if all of the solid can go into solution and dissolve, you're going to have interaction of the positively charged copper next to the oxygens. They're going to want to be next to that negatively charged oxygen, or the partial negatives on the oxygen, and the sodiums are going to be next to these partial positive hydrogens. So when this happens, when you go to the dissolved state, you're going to go from a solid form into the aqueous form. This is different than changing from the solid state to the liquid state. You do not have liquid copper nitrate. You have an aqueous form because it's dissolved in the water molecules. The liquid state, there's no water that's going to be present. It's just going to be the liquid form of the copper nitrate, right? That copper nitrate, if we heat it up, it'll eventually melt. That would be the transition to the liquid state. The aqueous state means that there's water present and that this molecule is dissolved. So in this case, it's separated into the ionic forms of the molecule. So that's dissolving in solution. So some ionic compounds actually form solid hydrates, which means they incorporate some water molecules into their solid structures. And so we will actually see this in the lab. You'll see an example of copper sulfate. Copper sulfate can actually take on water. So can calcium sulfate. So for each calcium sulfate molecule, there's going to be half a water. So actually this formula, you'd have 2 calcium sulfates for every full water molecule when you form the hydrate or the crystal structure for this molecule. Now this is still in the solid state, so it's not going to look like a liquid even though there's some water in there. The water is going to be incorporated into the crystal lattice of the solid structure. So when you have solid hydrates, the water is going to be represented in the molecular formula by this dot. So if this dot is present, this indicates that this is a solid and that water is forming part of the crystal lattice. So if you have ionic compounds that can really strongly attract water and pull water vapor from humid air to become hydrated in this type of fashion, they're called hygroscopic. So hygroscopic compounds are going to be able to pull water out of the air, and it's going to form into the crystal lattice. So those are solid hydrates.